Okay, we're going to take a look at number 11 here. It says for a certain strain of bacteria, K is 0.872 when T is measured in days. How long will it take 9 bacteria to increase to 738 bacteria? So obviously they're giving us K in this one. Okay, so we know we're going to kind of use, and I'm going to do number 11 up above here. So I'm going to go that we're going to use the equation y equals A times E. Now, is this growth or is this decay? Is it getting bigger or smaller? Well, we're getting from 9 bacteria up to 738, so it's growing, or the amount of bacteria is growing, which means it's growth, so that's going to be e to the positive kt power. There's the equation we're using. Now, we're going to put in 0.872 for K, okay? 9 bacteria is going to be my initial amount. 738 bacteria is going to be my ending amount. So I'm going to have 738 equals 9 times e to the 0.872 t power. So there's plugging the info in from our problem. Now, when we're going to solve this, when you worked on solving these, this one is dealing with base e, so eventually, when we're trying to solve for t, which is an x up there in the exponent, we got to get base e alone first. This is why we went through all those steps to solve. So we're going to divide both sides by 9. So if I take 738 divided by 9, that's 82. And that's equal to e to the 0.872 t power. Excuse me. Now we're trying to solve for t, which is up there in the power of that base e. We're going to do natural log of both sides. So ln of 82 equals ln of e to the 0.872 t power. Now remember, why are we doing that? Because that cancels out. So I really have, and to save myself a line, I really have 0.872 t is equal to ln of 82. Well, we're going to divide by that 0.872 on both sides. So I get t is about, and if you take the ln of 82, and I would do that on your calculator, okay, hit equals, then divide by your 0.872, that's going to be about 5.1. So we're at about 5.1, and we should label our answer here, and it would be days. Okay, let's go on and do number 12. So radium-226 decomposes radioactivity, and it's half. The time it takes for half the sample to decompose is 1,800 years. So that's half, its half-life, the time it takes for the sample to decompose, that's a typo there, that should say its half-life, okay, is 1,800 years. Find the constant K in the decay formula for this problem. So they're kind of telling you which one you need to use here. We're going to use y equals A times e to the negative kt power. And we're trying to find K, so that's going to be what we solve for, which is up there in the exponent on base e. Now, they don't give you a specific amount, okay, when we're dealing with A and Y here, but it's dealing with half-life. And so basically, you could make up a couple amounts, or you could just say that the ending amount is going to be 1/2 of A, and A is going to be the initial amount itself. And watch what happens when I do that. If I put 1/2 A, or I'm going to put 0.5 A in over here for my ending amount, and A times E, and we're trying to solve for K, and T is 1,800, so it's e to the negative K times 1,800, so it's going to be negative 1,800 K right there. Notice what happens when I divide both sides by A. They cancel out. So I'm really left with 0.5 on the left equals e to the negative 1,800 k power. Now I'm going to do the ln of both sides. And I'm going to bring it down here. So I'm going to do the ln of 0.5 equals the ln of e to the negative 1800k. Forgot a 0 there, but that's 1800. That cancels out, so I get negative 1800k is equal to the ln of 0.5. And then I'm going to divide by negative 1800 to find k. So I'm going to take the ln of 0.5 equals on my calculator, divide by negative 1800, and we get a pretty small decimal here. K is about 0.000, so 3 zeros, and then 385. And so I went to 6 decimal places there. And I would suggest doing that when you have those 3 zeros out in front.